Hi everybody, today I'll show you how to do problem number 28 from chapter 11. It states, the distance between the centers of the wheels of a motorcycle is 155 centimeters. The center of mass of the motorcycle, including the biker, is 88 centimeters above the ground and halfway between the wheels. Assume the mass of each wheel is small compared with the body of the motorcycle. The engine drives the rear wheel only. What horizontal acceleration of the motorcycle will make the front wheel rise off the ground? Alright, so here is my diagram for the problem. Okay, so I got lazy. I drew my motorcycle kind of like a car, but you got the idea. So I'm gonna say the motorcycle is traveling in this direction. The center of gravity for this motorcycle is that dot right there, which is 0.88 meters above the ground, or 88 centimeters. The distance between the two wheels is 1.55 meters. And since it's going in this direction, the wheels will be turning clockwise, which means the friction force will be opposing the rotation, which will make it be going to the right. There's also a normal force acting upwards on the wheels, and there's also the weight, as I've drawn right there. So to solve this problem, we're going to start with our sum of torques equation, which is that. Now, looking back at the diagram, we want to see when this motorcycle will start raising its front wheel and angling upwards. So the instant before that, however, there will be no rotation, or the motorcycle will not rotate at least. So therefore, the angular acceleration will be equal to 0. Then, I'm going to give myself more room and write this over here. Therefore, 0 is equal to the sum of all torques. Now, what torques are acting on this? I've drawn some of them here. If we think about what's happening in this scenario, the motorcycle will begin to raise, the front wheel will begin to raise off the ground. Therefore, right before that happens, the normal force will equal 0, and since it's not touching the ground anymore, the friction force on the front wheel will equal 0. What forces are still left? There's the friction force on the back wheel, normal force on the back wheel, and then the problem states that the mass of the wheel is much smaller than the body of the motorcycle. Therefore, the weight of the wheel is going to be much smaller, making it insignificant compared to the body. Therefore, we are just going to leave it out and just consider the weight of the body of the motorcycle, which will be our last force that we deal with. Therefore, we have 3 forces that we're dealing with, just this one, and the forces acting on the back wheel, and besides the weight of the wheel. So the way we're going to write this is we're going to deal with the friction force on the back wheel first. So R times the friction force sine theta. If you use the right hand rule, your thumb curls inward, which means it's positive. Now we find the torque for the normal. Oh, I should probably say this first. We are going to assume all torques relative to the center of gravity, so that's going to be the pivot point of the system. So or the axis of rotation is better for me to say. Okay, so going to the normal force on this wheel, using the right hand rule, you curl your thumb or your fingers outward, which means you'll be going in the negative z direction. So that's going to be negative or minus r times the normal force n sine, and I'm going to use v now. And the last force is the weight of the body of the motorcycle, and that's just going to be written as r times the weight times sine. I ran out of variables. I'm just going to use x. Alright, so now I've also drawn two more diagrams. These are both the back wheel. So, and this one is theta. That's phi for just to differentiate between the two. So what we're going to say is sine theta is equal to 0.88 over r, which means r sine theta is equal to 0.88 meters. Down here, sine of phi is equal to 1.55 over 2 meters over r. Therefore, r sine phi is equal to 1.55 meters over 2. And we are going to use these right now. So, looking here, we don't know what the friction force is yet, but we know r sine theta, which we just found here. We said it was 0.88 meters. So this is going to become 0.88 meters times the friction force. Over here, r sine phi, we found that too. R sine phi is equal to 1.55 meters over 2. So, times the normal force. And then here, for the torque dealing with the weight, this is being applied directly at the axis of rotation. Therefore, there is no r. R is equal to 0, which means this is just going to be plus 0. I'm going to write this off to the side way down here. Okay, so if we sum up the forces in the y direction of this system, we are going to see that there are just two. There's the normal force going upwards here and the weight going downwards there. Therefore, we're going to say normal force minus weight is equal to ma, where acceleration in the y direction is equal to 0. Therefore, n is equal to mg. Now, summing up the forces in our x direction, we see that there's only one. There's friction force on the back wheel going in the positive x direction. Therefore, the friction force is equal to mass times acceleration. Okay, so going up here, we're going to plug that in now. So, as we just said, friction force is equal to mass times acceleration. I'm going to put that in. The normal force, which we found below, we said is N is equal to mg. I'm going to plug that in. Also going to change this. 1.55 over 2 is equal to 0.775 meters. That times mg for the normal force. Now, what we can do is we are going to move this to the other side of the equation. Let's see, not much room. I'll try to squeeze it in. There we go. Now, then we can divide out the mass. Solving for A, we get 0.775 g, which is 9.8 meters per second squared, all over 0.88. The units for these coefficients is meters, so it's going to cancel out anyways, and your answer would leave you with 8.63 meters per second squared, and that is your answer for the acceleration in the horizontal direction.